Okay, so this is the exam 2 review for vibrations. And what we're going to do is we're going to run through a couple things. The first thing is just going to be a broad strokes overview.
Wait, I think you're gonna do the other.
Yeah, I'm just writing this for me and I'm going to work on there.
Yeah.
Overview. So where we're going to talk about our system procedure for solving. Linear algebra review. We're also going to do a review on the eigenvalue problem. We are also going to be doing after this, we're going to cover a past exam. And then we're going to work on any questions. Okay. So the main theme of this section of the course is about N-DOF systems. And what DOF stands for is degree of freedom. If we have a mass spring system, let's say, with more than 2 masses, like, for example, we could say a mass spring system with 2 masses, where we can ignore friction, and 3 springs. So we can start off by saying that this is M1, this is M2, this is K1, this is K2, and this is K3. So we would call this a 2-DOF system because there are 2 unknowns you need to solve for, and that is the position of mass 1, which is x1, and then mass 2, which is x2. You can sort of think of it like if there's 2 masses, there's 2 degrees of freedom. If there's 3 masses, there's 3 degrees of freedom. At least in this type of case, that's what it's going to be. The degree of freedom is not, this can move left and right, so that's 2. No, this can move either left or right, so that's going to be 1 degree of freedom. Both of these are one-dimensional with 2 masses, 2 degrees of freedom. Okay, so now we have our system set up like this. Our next step is going to be writing our system of equations algebraically. And so I would recommend doing that with the free body diagrams. So step 1, free body diagrams. So I'm going to go ahead and draw one for mass 1, where we have x1 going this way. So if I did a positive displacement, which would be to the right in this case, I would experience a force from K1 that would be going to the left, because stiffness always restricts displacement. So I'm going to draw this right here, where it's K1, x1. And then, if I push it this way, I'm also going to get a resistive force from K2. Now the important thing to remember when you're setting up these systems is that if I, let's say, moved M1 and M2 by the same amount, K2 would not change length. Would you all agree with that? So it's the compression and the tension of the spring that causes that force. Therefore, it can't be just the position, K2, X2. It has to be the relative distance between these 2 masses that causes the force in the spring. So we would write another left force that's K2 I want to say x2 minus x1. So there, that is our mass 1. And then mass 2, let's see what we have. If I move it to the right, I'm going to get a compression from K3, which is going to also go left. So that'll be a K3, X3, and then a K2. Sorry, this will be X2. K3, X2 minus X1. Alright, so now we have our free body diagrams for each of the two masses. Now the next step we're going to do is we're going to write a system of equations. It's important that you make sure your signs are consistent with this. So I'm going to start out by saying the force on mass 1, Newton's second law, is going to be equal to m1 times x1 double dot. And in this case, all we're going to do is just write all the forces we have right here. Notice that these are going to the left, so they're both going to be negative. And so I'm going to write negative k1 x1 and minus k2 parentheses x2 minus x1. All right, there's our first equation, and let's write the second one. F of 2, or the sum of the forces on body 2, is going to be m2 x double dot of 2. Notice how x2 is also to the right, and these forces are going to the left, therefore they're both negative. Therefore, we're going to have minus k2 x2 minus x1, okay, and then minus k3 x2. All right, so now we have a system of equations for our system here. What I'm going to do is I'm going to instead rewrite these as x1 minus x2. x1 minus x2, x1 minus x2. You see, even I'm getting inconsistent here with my definitions. So x1 minus x2. x1 minus x2. Because k2, if I move it this way, x1 minus x2, whatever. It just has to be the relative displacement between those two. And if you put it one way versus the other, like if they're both positive, if they're both negative, it's still going to be a distance, which is always going to be positive. So we're just, for convention's sake, we're going to put it x1 minus x2. All right. So right now we have things split up, or we have coefficients of k with combinations of x. And what I want to do is I want to rewrite this to where I have it in terms of x's. So I'm going to move this over here and say this is going to be minus parentheses k1 plus k2 x1, and then distribute this negative sign, plus k2 x2, and this one will be, looking at x1, that's going to be a negative k2 x1, distribute this negative, and then that negative, and you're going to have a minus k2 plus k3 x3. Alright, so now we've recombined our equations, or we've redistributed our terms so that we have an x1 term with a combined coefficient, x2, x1, and an x2 in both of these equations. Now, the next step is going to be putting it into matrix form. So, I can take this blue right here, And since I have an x1, x2, x1, x2, x double dot 1, x double dot 2 in each of the equations, I'm going to rewrite it in matrix form like so. I'm going to have, what I'm actually going to do is I'm going to take all these, add them on the other side to where it's like these x dot terms plus these terms equals 0. So in that case, the matrix form is going to look like this, plus kx equals 0, where m and k are matrices, and then x double dot and x are going to be vectors. So when I do that, I'm taking a look at this top equation. I have m1 for x double dot of 1, but I don't have any x double dot 2 in this equation, so the next term is going to be 0. Same thing here, there's no x double dot 1 term, so I'm going to have a 0, and then there is 1, so I'm going to have m2. That's our mass matrix right here. And so then I'm going to have x double dot of 1, x double dot of 2. Alright? And then for this blue right here, I'm going to have, oh, I did not do this well. Alright. I know what it is. Pretend like that's still up there. We're going to erase these and arrive at, looking at the coefficients, we're going to have k1 plus k2 minus k2 minus k2 and then k2 plus k3 for our stiffness matrix. And this equals 0. Now we've arrived at our ODE in matrix form. And so this is probably the most difficult of the procedure in my personal opinion. There's so many opportunities to confuse your signs. And so what I'm going to do is I'm going to erase the rest of the system because now we fully characterize the system within this ODE. We've done what we need to do. And now we're going to do a little linear algebra with this.
Would you recommend like deriving this each time or just memorizing this form?
Well, each system is going to have a different type of mass and stiffness matrix. So it's good to double check. Like if you're asked on an exam, here's a system, go ahead and write its matrix form ODE, then you're going to want to do this procedure. So just remember, it's free body diagrams, systems of equations, reorganize your coefficients so you have one x1 term, x2 term, x3 term in each equation, and then put that in a matrix form. So up here, I'm going to write m1, 0, 0, m2, x double dot 1, x double dot 2, plus k plus, or k1 plus k2, minus k2, minus k2, and then k2 plus k3. And finally, you're going to have x1, x2 equals 0. Alright, so what we're looking for is instead of analyzing one mass to have its own natural frequency, both masses are going to affect each other, which means this is a set of coupled equations. And so what we're going to do is, instead of trying to find each natural frequency and each amplitude, whatever, individually, we're going to attack them all at once. And the way we do that with matrix form is we're going to try and find the bulk modal properties of the system. And the way we do that is something called the eigenvalue problem. So the eigenvalue problem, by definition, is this. An eigenvalue is you can have a matrix times a vector. So this is matrix notation, this is vector notation, is equal to a constant times that same vector. This is the definition of an eigenvalue, so I'm going to write vectors, if I could spell, vectors, and then this is going to be a matrix and then this is going to be our eigenvalue. Right here. So we can express a matrix as a single constant value. In fact, dependent on the size of our matrix, we can have multiple eigenvalues, but they all do the same thing. So, what we want to do is we want to get it into this form, where we're going to have